Hi everyone, I'm Chitra R going to present our paper entitled TMS Crossbars with Tactile Sensing. My co-authors are Ms. A.R. Ashwini and Professor A.P. James. So this is a brief outline of our presentation. So this TMS crossbar, it finds major application for tactile sensing or sense of touch, which involves sensor arrays, and it enables a specific surface area to be monitored. The sense data are transmitted by a large number of cables or wireless modules for neural computing. This adds to the weight and complexity of the entire system. So the main objective here is to propose device intelligence at the sensor level, and which is not investigated before in the literatures. So our main objective is to design an intelligent edge AI computing solution to process the sense data at the sensor level in analog domain. So efficient integration of the sensor unit next to a Memristor neural network is the main objective of this paper. So for that, we propose a TMS cell configuration. So figure 1 shows a TMS crossbar array with 2 inputs and 4 outputs. So in the crossbar, each cell consists of one sensor, one memristor, and one transistor, and thus the name TMS. The effective conductance of each cell is the parallel combination of effective conductance of sensor block, memristor, and the transistor. For TMS configuration, we can there are two possible configurations for the TMS. So the first one is 1T, 1M, 1S cell configuration, and the second is 2T, 1M, 1S cell configuration. So in order to sense more features, horizontal readouts can also be included for this TMS crossbar array. So uh, if we are including the horizontal readouts also, for 1T, 1M, 1S cell configuration, it results in current leakage, which is shown in figure 2A. Whereas for this 2T, 1M, 1S configuration, we can considerably reduce the leakage current since we have two transistors in each cell. One transistor act as a switch in the vertical line, and the other transistor act as select switch in the horizontal line. Uh, so the neural computing capabilities of the TMS crossbars are explained with Braille character recognition system. So for Braille character recognition system consists of a neural uh, sensory patch and neural computing capabilities. So the first layer is implemented of the Braille system is implemented with TMS crossbar array, and the subsequent layers with 1T, 1M memristor crossbar configuration. So each Braille character is represented with 6 dots: D1, D2, D3, D4, D5, and D6. So for in this paper, we implemented 125 different symbols in this Braille system, and these 125 symbols are categorized into four different groups, and here the dot D7 and D8 represent the identifies the group number, and the uh, corresponding implementation with TMS crossbar array is shown in figure 3B. So here each would represent uh, one cell in the Braille system. So for the force sensor, for a spy simulation, we used an equivalent circuit of FLX A505 force sensor, which is shown in figure 4A. The force dependent variable resistance is modeled as R1 of F is equal to 1 by 1.5 micro into force plus C, where F is the applied force and C is the bias voltage. Figure 4b shows the resistance and conductance variation with applied force of FLX A505 force sensor. So the figure 4b shows that as force applied force increases, resistance reduces, conductance increases, and hence the output voltage also increases. And the supply voltage is 0.5 volt, and the reference force for symbol detection is 20 lps. So Memristor crossbar design. So the first layer is implemented with a TMS crossbar arrays, and the subsequent layers with Memristor crossbar design using 1T1M cell configuration, and transistor switches are modeled with 22 nanometer high-K PTM models. Memristor model, no multi-stable switch Memristor model with R on equal to 1 kilo ohm, R of equal to 100 kilo ohm. The activation functions used Reliev and Softmax at the output node. So this figure 5A shows the equivalent circuit diagram of Softmax activation function. So Softmax activation function mainly consists of an exponential layer, summation, and the division. So the circuit level representation of the exponential block and division block is shown in figure 5b. The theoretical output value, the calculated theoretical output value of this softmax activation function is given in the equation. So results and discussions. Evaluation of the TMS crossbar arrays and analog computation of Braille system were evaluated using the SPICE tools. So figure 6a shows the effective conductance analysis of TMS crossbar array variation with respect to membrane. So figure 6a shows that as the membrane increases, the effective conductance reduces. Figure 6b shows the effective conductance analysis of TMS crossbar array variation with respect to applied force. So as force increases, the conductance increases, and variation with respect to different resistance values is also shown in figure 6b. So for Braille system evaluation, we have like modeled the TMS first layer of the TMS crossbar arrays. So we have generated a data set of 125 a data set of 750 samples of 125 Braille characters, and the table 2 shows the recognition accuracy of the analog and binary TMS crossbar based on Braille recognition system. The performance accuracy with variation of noise is shown in the table. Uh, so the results in the table 2 shows that the analog system performs better than the binary system in noisy environment, uh, because this binary system is prone to errors. And table 3 shows the Braille character recognition, a comparison with the previous Braille in the Braille works in the literature. So this table shows that our proposed method shows improved accuracy and scalability, scalability in comparison with other works in the literature. And with the proposed one, we were able to implement 125 Braille characters. So the next result shows the output of the Softmax activation function of the Braille system. Figure 7a, it is a comparison of software, hardware, and theoretical output of the Softmax function for like a small letter t, for the Braille character T and 9, and figure 7b, Softmax output of the Braille system without noise value uh, for different characters belonging to group 1, group 2, group 3, and group 3 and group 4. And figure 7 C shows the output of Braille recognition system in a noisy condition of sigma square is equal to 0.05, and 7D Softmax output of Braille system with a noise of sigma square is equal to 0.1. So like from 7C and 7D, it is clear that as the noise increases, as the noise increases, the false detection accuracy reduces and false detection increases. Right. And table 4 shows the power consumption and area of TMS based Braille character recognition system, a comparison between series and parallel processing. So the output of the Crossbar can be parallel processed or serial processed. Serial processing is, so the results in table 4 shows that the series processing is power efficient in comparison with parallel processing, because series processing we are doing it with the one sense amplifier rather than multiple sense amplifiers. That's why that power efficiency comes in for the series implementation in comparison with parallel implementation. So binary systems require data converters, a interface and adder circuit, which requires high area and power in comparison with analog representation. So this TMS, so from table 4, it can be like analyzed that the analog series representation is showing better area and power constraint representation for this TMS crossbar array. So conclusion: TMS crossbar array transforms the tactile sensor patch to a system with sensing and analog neural computing capabilities. The Braille character recognizing system with the proposed method shows better accuracy and scalability. Benefits of analog implementation of TMS is substantiated in terms of accuracy, area, and power requirement. So these are references. Thank you.